now I'm using R instead of H. All right? So I've got a buried sphere here of radius R. It's got a mass contrast of delta M. I'm at Z, and the difference between a vertical and my measurement position, which is over here, you can see the gravimeter there, is X. Okay, so I have obviously a gravity anomaly. This is wrong here. This should be vertical here. Delta GZ should go down like this. So there's an X gravity anomaly out of the plane. There's no Y gravity anomaly because we're assuming this is 2D. And there's a Z gravity anomaly vertically, obviously. So we can look at the math of that pretty easily. The change in gravity is just going to be G delta M over R squared. We know that. And so we can change delta M to a density contrast multiplied by the volume of the sphere, right? And then we can put in an equation for the volume of the sphere. And then we can basically differentiate with respect to R squared, and we get this, then we can basically say, okay, R squared is X squared plus Z squared, right? So that's the gravity anomaly in the direction of the sphere to the surface location. So this is not, if we go back to this, right? This delta G is this way. It's a vector, right? So these arrows are really just vectors. So delta G is pointing there, and what we want is the vertical change in gravity. So what do we have to do to this equation right here? How do we convert this to the vertical? Multiply by cosine, right? So we want to multiply this by cosine theta, right? There it is. And cosine theta is simply Z over R, right? If we go back to this triangle here, cosine theta is Z over R, adjacent over hypotenuse. So we put that in for cosine theta, and we get this expression now. And now notice that this is the gravity anomaly in the Z direction. And that's what we always use in looking at gravity anomalies. So we move along here, and we've got the volume multiplied, we've got basically the volume multiplied by delta rho there. And this is our expression for the vertical gravity anomaly multiplied by the volume, or basically the vertical gravity anomaly. So we can rewrite that like this. All right? Make sure that that's correct. Yeah. I'm not sure that is correct. Yeah, it's gotta be. This is just doing a bunch of math and simplifying it. We could always write it as Z over X squared plus Z squared. We could combine these and make this to the 3 halves and leave a Z out there. There's all kinds of different things we could do to simplify that. So let's go back then. Well, let's do this. Okay, for an arbitrary sphere of density contrast rho and radius r, we get a gravity anomaly that looks like this. And if you fill in some values there, what you'll find is that the depth of the sphere anomaly is equal to about 1.3 times the distance from the maximum value of the gravity to its half distance away. Why does that happen? Oh. distance should be where the value of gravity goes down to half of what it is at the maximum. All right, so this half width is where the value of the gravity goes down to half of the maximum, and then you can calculate z as 1.3 times the half width. Now let's go back to this. So now that I know what the response of a buried sphere is, and again we're changing variables here, I can basically calculate the vertical gravity anomaly of any topography, of any geology whatsoever. All I have to do is take all these little spheres and add them up. Really, that's all I need to do at this point, where z and h are variables, right? So you can imagine a pretty simple Fortran loop. This is simply a triple summation. So let's say that I had a surface like this, and I have a bunch of little squares in here. And these are, we'll call them delta rho of xi, yi, and zi. All right. So then, and this is z prime minus z, which is basically, this is elevation z, and this is equivalent to z prime. And h is obviously x prime plus x prime minus x blah, 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 blah. So then I can basically do three for loops, right? I can do for I equals 1 to n, j equals 1 to m, k equals 1 to n, and then I can basically simply multiply delta g, g z equals some kind of sum, right? So I basically just add these things up for summation, right? And then I have another summation down there. Simply accumulate that gravity anomaly due to an arbitrary shaped surface. And that's how I, in reality, correct the data down to a surface as well. That's how it's done in the computer. X, Y, Z being the observation. Okay, let's take a look at a couple of interesting facts.
Professor,
Yeah.
you had delta density in there. You have to measure the take borings or anything like that?
Excellent question again. So what do geophysicists typically do? Yeah. Basically what we would do, literally, in most cases, is we would get some surface geology. All right, we'd say, I think it looks like that. Oh, I think there's some kind of fill here. And then I'd basically discretize the model. Maybe this is rho equals 4.4. This is rho equals 2.7. This is rho equals 2. So I'd have a little block up here that way. I'd have a few blocks this way. I just make them up. I just manufacture out of thin air that wonderful model. Because I know something about the geology. Right? That's why it's not physics alone, it's geophysics. Good question, really good question. Okay, so in this case, this is a really interesting feature. So here's the depth in kilometers of a density contrast. Okay? And in this case, we're going to assume that the density contrast at that black thing there is the same. Density contrast is the same for the first anomaly, for the second one, for the third anomaly, and the fourth one. Each of those models gives the same response at the surface. Each of those models, remember that, each of those models assume that your geology is relatively, if you assume you have a sphere down here, that'll create the anomaly. You could also have a little lens up shallow of the same density contrast. If we throw in the fact that density can vary as well, we can do anything we want with this thing, okay? So gravity inversion has to be constrained by some understanding of the geology. It simply doesn't work unless you know something about the geology. Okay, let us go down to this example. So suppose we are looking for a buried sphere. Okay. Let's suppose we're looking for a hole in the ground. If we have a density contrast, obviously if we have a positive gravity anomaly, we're going to have that. If we have a negative gravity, we're going to have that. Notice, though, that we can basically change the anomaly by